Today I'd like to talk about Amperes Law, a very useful equation for finding the magnetic field of an object at a specific location. The equation that we're most familiar with is the integral B dot ds equals mu naught times I enclosed. However, the more commonly accepted equation is that it equals mu naught times I through plus mu naught epsilon naught times the time derivative of the electric flux.
What this means is that you must take a closed loop, any closed loop, and attach to that loop an open surface such that current can go through this. This can be any open surface such as a circle or a shopping bag, and this term represents the time derivative of the electric flux or the electric field going through some area, and is also known as a displacement current, which symbol is I sub d, and this term is also known as the conduction current.
So I want to take you through a classic problem to understand this concept. So let's say we have a capacitor being charged with a constant current I sub c, and it has a radius r, and also the electric field goes from left to right inside this capacitor. We want to find the magnetic field at a distance little r greater than big R above the center of the capacitor. And let's assume that the electric field outside the capacitor is 0.
To solve this problem, we must attach to it a loop that goes through the point in an open surface, whether it be this circle or a shopping bag. The first one we're going to look at is the open surface with the shopping bag. Using the shopping bag, the second term is equal to 0 because the electric field is a constant 0 inside the shopping bag since it's outside the capacitor. So to find the magnetic field, we just do that B times 2 pi r is equal to mu naught I sub c, and we solve for B, it's equal to mu naught I sub c over 2 pi r. Now we will use the circular surface, and we should expect to get the same answer as we got with the bag. Looking at the circular surface, no current passes through it, so the first term this time is actually equal to 0 instead of the second term.
So we get that the closed integral of B dot ds, or just B times 2 pi r, is equal to the time derivative of the electric flux, or dE dt times area times mu naught times epsilon naught. We can just use dE dt times area because E is constant over the whole area, so we could just take it off the integral. And we know that E is equal to sigma over epsilon sub naught, and sigma is equal to just Q over A. And since Q is a function of time, we could write Q as the initial charge plus the current times time. So taking the derivative of that, we get that E is equal to I sub c over area times epsilon sub naught. And multiplying that by area times mu naught times epsilon sub naught, we get that that's equal to I sub c times mu naught.
And now doing B times 2 pi r is equal to that. We get that B is equal to mu naught I sub c over 2 pi r, which is the same answer as we got before.